Welcome back. Make sure you have your model kits. Better yet, have your cyclohexane ring built with all of the H's attached. Now what I want you to do is swap out all of the H's that are axial and replace it with a colorful group. So look at your model kit. Do you have a lot of green, purple, orange? Pick one color ideally and replace whatever you have 6 of. Replace all your axial H's with that color because we're going to track this with the color. And so it's going to look like mine when you're done. And what do I notice when I do that? So my axial H's, so if I grab them, I'm grabbing all the orange atoms. And around the periphery, I have all the white ones. Those are the equatorial. So I'm color coding it. My axial are all orange. Let's draw this chair on paper. And we're going to look at this a lot more closely. So I'm going to view it so that I can start with this chair. I don't know why, but that's my favorite chair. That's the one I start with as opposed to the other one. Maybe it has something to do with being right or left-handed, not really sure. And then in this chair, if you slant your bonds to be viewable that way, then you're going to have the up carbon just to the right, the one that's in the front, to the down carbon in the back. Okay, now fill in all the axial bonds first. That's easier. Find all your up carbons. All those axials are up. It's every other. Those are the 3 axial up. Let's color code them. I'm going to use red because that's the closest thing I have to orange. So it should look like that, right? Now let's fill in the down ones. Every other carbon's down. Oops, I did not want to erase. Every other carbon's down. So that one's in the back, and there's one there. So you should have 3 up, 3 down. So far, so good? Equatorial time, grown. But we need to practice. Okay, equatorial, parallel to other side. Since they're white, I'll just circle it with the white, okay? In fact, I won't even draw the H's because I'm trying to make this as simple looking as possible. Equatorial, right? Equatorial. Equatorial and equatorial, parallel to the other side, parallel to the other side, okay? So those H's are along the equator and the red are up and down. Now when you made sure you made that chair, you did so by saying, okay, that this carbon right here, you're going to be up. You're going to be down. Let's number them so we could track them. 1 was down, 2 was up, 3 was down, 4 was up, 5 was down, 6 was up. But what we know is that those carbons rotate and change conformations in solution. They don't stay, in other words, 1 does not stay down. It likes to also go up. That's how we get the other chair. All right, so let's do that. Pick a reference carbon. Okay, so I just went and raided my kid's sticker drawer and I chose a star, but you could get a piece of tape, something, or a label or whatever. So I have this nice shiny star. That's my carbon 1. So put a little star there, just so you can follow along with me. Now I am going to do my chair flip. To flip your chair, that doesn't mean we flip it over. Not that simple. Nope, it's an equilibrium process where all up become down, all down become up. So I'm going to indicate what's going on here. Notice my star is a down carbon, down below the plane. So pick that for your reference. Now let's push the down carbon up, and then that means its neighbor carbons have to go down. Work your way around the ring until all former up carbons are now down carbons and vice versa, okay? So if you need to put stickers on all up carbons, right, or all down carbons until you get that right. Okay, so now, notice what you got here. I'm going to grab all my axial H's to make sure they're all lined up. Notice my equator is orange. It used to be white. My axial positions are all white. That's how the chair flip happens. Notice my carbon 1 is no longer down, it's up. Hence the other chair. Let's draw the other chair. The other chair needs to be drawn this way. Okay, so now let's number those carbons first. I had carbon 1 in this nice little corner. I tend to start in corners with these things. But notice that this cannot be carbon 1 anymore. Why? This is a down carbon. That's a down carbon. Is carbon 1 down? Nope, it's pointing up relative to its neighbors. Has to be an up carbon. So when you do a chair flip, your numbering starts at adjacent to the corner you started on. Okay, so if you start in this corner, you have to kind of move it over one. It doesn't mean that it like literally moved over. The perspective's different. So now if I want to look at the chair that way with carbon 1, right, I have to have that carbon moved over because it's not down. So carbon 1's now here. I'm just going to put it here, but I could have just as likely put it here, right? So, but I like to often go clockwise, so I'm going to do that. 1, 2, 3, 4, 5, 6. That's now carbon 6. Carbon 6 is down. It used to be up. Fill in all those groups. Fill in what we see. In our model, we see 3. All up carbons have a white up carbon. Oops, let's go back to the black. White atom up, white atom up. So you alternate. 1, 3, 5, white atom up. 2, 4, 6, white atom down. Now let's fill in our equatorial positions. Let's at least do the bonds, then we'll do the colors. 2 is opposite the bond 3, 4, so it's parallel to that. 3, carbon 3, has equatorial parallel to 1, 2. 4 goes this way. 5 is this way. 6 is that way. Fill in those colors. We have an orangey reddish equator like our model. We have successfully done a chair flip. So things to note in a chair flip. Up carbons become down carbons after the chair flip. What else happened? All axial groups became equatorial. All equatorial groups became axial. Okay? We did this exercise with generic colors so that we can adopt it to any other substituents on there. You're not going to have cyclohexane alone. It's going to have substituents most of the time. So let's start expanding this template, the color code template, to see where things like a simple methyl would go. So we'll often see the chair drawn this way for us without all the H's drawn in, and that's up to us to remember where they go. And then let's do this exercise where we just draw the chair flip. Okay, so that means I always recommend numbering your carbons. So let's number 1, 2, 3, 4, 5, 6. I like to give 1 to the one that has the group, just because that's usually my point of reference. I also like to make sure I fill in relevant H's. I'm not going to fill in all the H's on the ring. I'm going to fill in the H's that I'm tracking because the substituent is part of that carbon bond. So in other words, carbon 1, I'm going to write the H in there because I'm paying attention to where that methyl is going to go. All right, so carbon 1 is an up carbon. That means its axial is up, but we don't have it drawn in. That must be where the H is. Now, when we do the chair flip, notice since they're all going one way, they go the opposite way in the flip. Okay? And move those carbons over a notch because carbon 1 was an up carbon. It needs to be a down carbon now. So it can't be here in this corner like it used to be. It has to be moved over one because it's up here and it can't stay up. So it's got to be down. So that's now carbon 6. So now on this carbon, we draw the methyl and the H. I recommend drawing the H so that you don't accidentally draw a bad chair. And I'll show you a bad chair in a minute. Well, there's common problems that I'll show you. So equatorial site, axial site looks like that. Now, when we did the chair flip, this was an equatorial methyl that was also at the down position and down. Equatorial doesn't mean down, right? Axial, half of them are half the axial up, the other half axial are down. Hence, half the equatorial are up, the other half the equatorial down. So this is equatorial and down. So make sure you obey. Down stays down. even in chair flips, okay? So the methyl needs to stay there. But notice how it's axial now. That confirms we did the chair flip properly. Fill in your H, okay? We're going to draw the double Newman now. When you're asked to draw a double Newman with a substituted cyclohexane, you want to avoid viewing it so that in a way that puts these groups on a middle carbon, because it's not part of the Newman. You want the middle carbon to be part of the Newman. So once again, I'm going to put my eyes right here because I need to look down these bonds. All right, so let's do that here as well. I'll just do blue so it's a different color. Okay, so let's draw our double Newman. So carbon 4, carbon 2, carbon 1's in the back, 5's here. We're going to connect, 4 and 2 are connected at carbon 3. 3 is pointing up. In the back, 5 and 1 are connected at carbon 6. 6 is pointing down. Fill in the staggered framework. You need to make a Y. So if this is one arm of the Y, then the rest looks like that. The rest looks like this. Here's the other leg of the Y right there. There we go. Carbon 1 in the back has a methyl down. So look at carbon 1, it's in the back. These are the two bonds attached to one. One of them gets the H, one gets the methyl. Which one gets which? So because the methyl is down, of these two, you say this is above this bond. So the methyl has to be the one that's down, right there. So this is H. Everything else is H. So that was the hard part. Now we can just fill in H's. Now let's draw in the other Newman. Let's do the blue one. Our front carbon is up again, our back carbon's down. So our framework will look the same, front up, back down. Let's do that. So front up, back down, fill in the framework, those missing Y's. So it looks like that. Now, number your carbons. So we're looking from 3 to 4 in the back, 1 to 6 on the other side. 1 is connected to 3 via 2, 4 is connected to 6 via 5. All right, now let's draw in our methyl. Our methyl belongs to carbon 1. There's carbon 1 in the front now instead of in the back here. Our methyl belongs to carbon 1. Our methyl is still down. It's always down. I'm going to draw out the whole methyl this time. C, H, H, H. And then everything else is H. And if that bothers you that I didn't do it in the last one, I understand. I am very sorry. Let's just draw it out. Let's be consistent. C, H, H, H. There's a reason I'm doing this, by the way. Okay, so H, 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 H. All right. Now, we've learned that of all the conformations for cyclohexanes, chairs are the best. But we learned there are 2 chairs possible. When there's 2 chairs possible, is there ever a time that one chair is preferred over the other? The answer is yes, most of the time. So you're like, oh great, now I have to figure out which chair is better. And the double Newman helps you with that. Just like you figured out which conformation is ideal for straight chain alkanes, the double Newman kind of helps us with that. So what's going on here is we could see that when we have a bulkier group like methyl, anything that's not H is bigger, it's going to need more space. And just look at your model. Who is closer to other groups, the equatorial sites or the axial? Try to get the equatorial to touch. Try to get the axial to touch. You actually can kind of get close. I can actually even make that noise, right? But if you replace one of these H's with a methyl, which you might want to go ahead and do that, you'll see they can easily start to get really close to the other ones if they're axial, but not so much equatorial. There's less space in the axial position. In fact, who would it bump into? If this was a bigger group, Who would it bump into? You know what, let's just build it, because it'll make more sense if we build it. Build it. You know, sometimes I'm lazy too, and I feel like just visualizing it, and there's really no substitute for that. So I'll admit I have the same problem that I caution students against. You can't shortcut these things unless you're really in the next several classes. So, all right, here we go. I've just replaced one of the H's with a methyl. Now, this is really easy to do, the bump. And the methyl likes to freely rotate, and it's restricted because it's so close. Flip the chair, see what happens. You'll see you have a lot more space, okay? So what we are just learning from this example alone is that, oh, it's freezing a little. Here we go. That's the kind of symbol for bulky, unfavorable interactions. There's some bumping into the other axial group nearby. Notice this is a carbon 1 and 3. Carbon 1 has a methyl that's bumping into something at carbon 3. We call these 1,3 diaxial interactions. I'll write that down here. 1,3 diaxial interactions, or strain. Interaction sometimes sounds favorable, where strain is clearly bad, which is why we like to use the word strain these days, but some of the older definitions are interactions. Notice you may have numbered, you said, what if I called it ABC, or DEF? You still have a 1,3 relationship, right? They're 1, skip a carbon, 3. That's what it means when we say 1,3. It doesn't matter how you numbered it. You could renumber it starting with carbon 1 and arrive at the other one at 3. So 1,3 diaxial interactions means when two groups are axial, right? If one of the groups is big, it's going to experience unfavorable strain with the 3 carbon. So in other words, I can number this. I'm just going to draw in this axial, this axial, this axial. And if I decide to call this carbon 1, I can call it 2, 3, and I could call this one also 2 prime, 3 prime. And if this is a big group, let's even make something bigger, but I'll just draw H's. It's going to experience 1,3 diaxial interactions from both of them. Okay, so it's not just that one carbon, it's the other one as well. All right, so that's just something to be aware of. It's just not drawn in the double Newman because it's that carbon over there, 135. They all have those interactions with this methyl. Okay, so in summary, we can say chairs with large groups on axial sites are less stable than chairs with large groups on equatorial positions. Therefore, which chair is more stable? This one's better. No 1,3 diaxial interactions, which means that this is the more stable chair, which means if we're going to draw the arrows properly, the equilibrium arrows, get a bigger one going this way, a smaller one that way. It still flips. There's a distribution. So like everything in science, there's a spectrum, a sliding scale, and there's just higher percentage of the chair at any given time of solution with a methyl equatorial or any big group equatorial. Okay? What if we have lots of big groups, Dr. Meyer? Well, then you want to minimize the amount axial versus equatorial and put biggest groups equatorial if you have that choice. We'll get to examples with more groups here. So logically, as you increase the size of the group, you increase the steric strain. Sterics meaning bulkiness, right? So strain due to 1,3 diaxial interactions. When something has steric strain, it means there's no room for it. Steric hindrance is another word. 1,3 diaxial interactions. Okay, so for example, T-butyl, very big group. It really only exists in equilibrium this way. It doesn't even really flip because this is strongly preferred. So it's almost the only thing observed in solution. So you can get to one extreme end or the other, right? Where you have 50-50, no preference, or a strong preference for one or the other, or a slight preference. So we're not going to worry about those numbers in this class. In advanced organic, you'd probably do some calculations to do that if you keep going, but we want to get it conceptually right now. Okay, I've got some examples here. We're getting to the good stuff where we have more than one substituent. This is more representative of the problems we'll be doing. We got 3 of them for you to practice. I'm going to do one for you. You're going to do the other 2 and check back with me for your answers. Okay, so how do we approach this problem? We've got to translate the bond line dash wedge format of the cyclohexane that's substituted to the chair, and not just one chair, both chairs. All right, so let's start by drawing chairs. Draw them both. You've had lots of practice with that, I hope. And the other one. Okay. Now, how do we plop down those methyls? I recommend numbering your carbons next. I'm going to start with number 1 here. And I'll just keep going around clockwise. Notice I'm acknowledging that I went clockwise. If you number this clockwise and then you number that counterclockwise, you'll get confused. You'll need to just be consistent. There's no one right way. This is your own personal labeling system, like putting the star sticker on there. But just be consistent. So I'm going to start here with carbon 1, which also was random and my choice. I could have picked any carbon. But now that I've picked a carbon, I'm going to commit to it and go clockwise with my numbering. 4, 5, 6. Okay, now what happens in a chair flip, I know that carbon 1 is going to be not in that little corner right here anymore. It's going to be in one of these 2 positions. And I'm just going to keep sticking with my clockwise direction. So I'm going to let 1 be here now. I can't let it go here. That's confusing. If you started here, it's going to be here or here. But just to keep consistent with me going clockwise, I'll move it over 1 and then I'll continue my numbering clockwise. So 1, 2, 3, 4, 5, 6. So you'll learn there's a lot of right ways to arrive at an answer, but they could get confusing even though they're right. So the best thing to do is to develop a system and stick to it. Say, I'm going to go clockwise and stay clockwise, right? And then you'll kind of be able to follow along. If a friend you're studying with went counterclockwise, as long as they went counterclockwise throughout the problem, you could follow it. But you pick a system and kind of just stick with it. All right, now I'm going to draw in the axial and equatorial bonds, but not all of them because I'm lazy. Well, not just because I'm lazy, because I want to focus on the ones that are changing, not all of the H's that we don't need to draw in. So in other words, I'm only going to draw on the axial and equatorial bonds on carbon 1 and 4. So let's do that. So find carbon 1. Note that on this chair, carbon 1 is a down carbon. Therefore, I need to draw a bond straight down for that axial position. I don't know if that's methyl or H yet by this analysis. I'm merely filling out the framework. Carbon 1's equatorial position needs to be drawn in parallel to bonds 2, 3. Okay, now let's draw in carbon 4's axial and equatorial positions. Carbon 4 is a carbon that sticks straight up, so I need to draw an axial up. And it is parallel, its equatorial position is parallel to this bond here between 5, 6. So it's going to look like that. Okay? All right. So do I still know it's methyls and H's? Not yet, because I can't look at this and dare call any one of these axial or equatorial because they could be either. I also can't say wedges are always axial. They're not. Half the axials were up. Half the axials are down. That's the language I need, is up and down. So let's translate your mental framework to up and down now. I finished deciding what was axial and equatorial here. Now I'm going to decide what's up and down. Okay, so wedges mean up. Dashes always mean down. Okay, go to carbon 1. We've already discussed axial and equatorial, so let's put that on the back burner for now and think about up and down. Which of these 2 bonds is up? That one's above that one. It's as simple as that. That gets the blue group for carbon 1. The blue group for carbon 1 is the methyl. Do the same for carbon 4. It just so happens the H is above the methyl there. Now we're going to do a chair flip. And we need to draw in the axial and equatorial sites here too. So same idea. So carbon 1 is an up carbon now, so axial up. Carbon 4 is a down carbon now, so axial down. Parallel that one. Equatorial looks like that. Now, up always stays up. Carbon 1 has an up methyl. It's always up, even in the chair flip. It's the axial and equatorial that switch, but not the relative orientation. They always are up. So wedges translate to up, which is up in both chairs. See how that's true? Carbon 1 has a methyl above an H in this chair. It also has a methyl above an H in this chair. In this chair, the up happens to be equatorial. In this chair, the up happens to be axial. Carbon 4, that methyl better always be down. It's down. Of these two bonds, this is the down bond, which happens to be axial this time. Okay, so we have up 1. Now let's go back to thinking about axial and equatorial. 1 equatorial methyl, 1. Actually, we have 2 equatorial methyls, right? And here we have 2 axial methyls. Which one's favored? Obviously, the one with 2 equatorial, right? So that's favored. So the arrow is bigger this way. Okay, so I started with the middle one. I want you to do the one above and the one below. Compare to use the same analysis. All right, so maybe they won't be, sometimes they'll be equally favored. So if you don't get a difference, like if I had 2 groups, one was axial and equatorial, and on the other chair, one was equatorial and axial, same energy, different preference. So give those a try and see what answers you come up with. Good luck. I just want to see you rotate.